All right, okay, so spring break was a change, which was a change. It's not a break. Anyway, so we're going to talk a little bit more about generating functions because they're just so nutritious and fun. And we're going to talk about random bipartite affiliation networks, graphs, and the structures that result from this. So this is a very profound and important kind of thing, and we're going to look at the basic random network story. It's a very famous paper, 2001 paper by Newman, Strogatz, and Watts. I think it's Newman, Watts, and Strogatz. You know, it's got 3,000 citations, something like that, which is solid. Good, it's not bad. Remembering again that one citation is, you know, an achievement, 10 is heroic. Okay, so we'll work through that. I want to talk a little bit about diffusion. We're going to have some interesting asides. I'm going to talk about probability again a little bit, okay? And then we'll move on to contagion. We're going to do a lot more contagion. Yes? I need my tracking thing. All right. Thank you. Thank you so much. Yeah. Well, I had to find where it started. Yeah, okay. Thank you. All right. Now it's alive. Okay, good. And so am I. So, okay, this is assignment 7, Ethel the Frog. That's there for your enjoyment. Okay, number 3 might be tricky, but we can negotiate what happens with number 3. But that's good for you. Let's see. So I was going to show you a little bit about the new website, or the revised kind of website. So we have nice things now for the assignments. Yeah, all these good things. You know, and it does all the right things. I'm using Foundation, so that should, right? So it should plop like that if you're on a mobile. It's Foundation 5, which has 3 different things: there's small, medium, and large screens. And now I think they have 7 screen sizes because there are so many screen sizes. So you can set all these things. I went pretty crazy, and yeah, it was that fugue state thing again. So this is, wow, we're at UVM. Look at that, just charging off the surface. Oh, there are no things on the front. Come on, okay. Have you ever had, what's that? You never have trouble? No. Look at this. Look at that. Wow. All right, well, maybe there's something buggy on the front that I don't know about. I'll look at it. Anyway, episode. So this has changed. So now it's this kind of structure. You can just click on it. I hope it's a little easier to navigate. You can share pages with the little fun thing. These are still here. And yeah, and it's got all that good stuff. So it should go down to sort of 2 like this if you're on a phone. And now it's properly into a bipartite structure, right? So the slides are over here in another box. Oh man, what is wrong with this thing? This is so, I guess maybe it's me, but why would that be fast? Okay, all right. That one's just not loading, I'm sure. Okay, good. All right, so these are all here and they all do the right things. Now, if you dig into one of them, right, it should do good things, right? So let's say we're here. Wow. I mean, is it just sort of coming through a straw or something? Okay. Right, we'll do it twice. Okay, so now they're laid out like this, right? So they're going to be laid out like this. This is, sort of ultimately an archival object, summary and all these sorts of things. The video is here. It tells you which slides it's connected to. It's got a little navigation structure here. Bunch of Perl scripts do all these good things for us. Of course, the madness. And I have no idea why this won't load fast, which it does at home, but not at the actual institution. So you can click on these, and I guess I'll have them connected to assignments and things like that later on. So, all right, yeah, what is wrong?
Just a minor feedback thing.
Yeah.
Anytime you've got a clickable link in text, you've got a big word that has a link embedded underneath it.
Yep.
There's really not any context and color to it, so make it obvious.
Yeah, so the links could be colored in a better way.
Yeah, I don't know if there's another color.
No, that's very choosable. I went with a pretty minor kind of gray thing, but I can make that. All right. Okay. Okay. Good. Anyway, so make it easy. All right. Make links. That is fine. Okay. So hopefully, and I know you guys don't necessarily need to look at this site that much, but some of you do. Make links easier to see. And it may be years from now when someone says something silly to you about random bipartite networks or whatever, power laws or something, you can say, watch this for 3 hours and then come back and talk to me. I've had students go off, one went to LinkedIn for an internship and ends up having a big debate with the person next to them about power law size distributions for links or whatever, and clearly the other person had no idea. So, can point to things. Anyway, I think that's kind of, it feels like I did so many more things. But anyway, it's basically, it's just some scripts that just pile this stuff in. It's very nice foundation. This is essentially, if you go back to this, this is just like UL/UL list, LI for each object, and it just makes a nice grid and just populates it. It's really beautifully simple. Okay, which I complicated in funny ways. All right, so that's the site. So I'm going to go back and we're going to finish this bit on generating functions. We're going to pop out to an aside because we're going to have the little aside. It's going to be about probability, which will hurt. It always hurts. And that should be fun. Okay. All right. This is not where we are. We are here. And we're going to go to this bit. So we're going to have to remind ourselves of a few things, I suppose. And you can ask me which things. You can tell me what things you need to be reminded of. We need little signs in class. I know, so I came across this for middle school, that there are things like window wiper means it's all clear. So kids signal to the teacher or to each other, right? And like muddy or something like this, And apparently it works really well, Allows students to communicate to the maniac who's talking too much at the front. Did it work? Why no happy? Okay, come on. Boop. I don't want to do that. All right. Okay, so we figured out in this crazy business what the size of the giant component was, and that was a big deal, right? That's hard, and we actually figured out that we could determine the size of all of the finite component, or how, the probability of all these components. Come on, get out. But this last piece is the average component size. What are the sizes of these things? What am I doing? Yep, as planned. All right, good objects. Sorry, people. Okay, needed a new brain. All right, good. So, we're going to find the size of the finite components. We're just going straight back into this thing. So, remember this oddness that even when there's a giant component, we still have all these distributions, and we're talking about the finite components. Always talking about the finite components, which up until there's a giant component, up until that, if you've got a phase transition, up until that, everything's a finite component. Get a phase transition, there's one giant component. You can never have 2 or 3, right? Because the probability of them connecting is so incredibly large. It's 1. So you have a giant component, you have all these finite components around. That's what we're always describing. So we had these, we had P, we had R, right? So P is the distribution for degree. That's the basic thing. That's if you jump on a node, it's the probability that that node has degree K. If you run along an edge, we'll come back to that, we're going to use this again for this random bipartite stuff in a really beautiful way. Run along an edge, hit a node, what's the probability that it has K other friends? That's R. And then we have these analogous ones, pi and rho, and pi is the probability that your node is part of a finite component of size n, pi n is, and rho n is probably that there's a subcomponent of size n at the end of an edge. So if we've got this distribution, and either we can have the distribution or the generating function, this mysterious object, and we know from generating functions, once we have them, we take the derivative and set x equal to 1. That is the average of whatever the thing is, right? In this case, for us, it's the component size, the finite component size, right? So for f of p, differentiate once, set x equal to 1, that's the average degree. We're talking about component size here. We're looking at the pi distribution. Now, we could find this whole thing, which sometimes, we've sort of saw this example, right? Where it was a square root, it was a sort of a funny looking business, and we had to take a Taylor expansion, that stuff. That's cool, but and that was for the row one. But maybe we can avoid that altogether. And this is an equation that, right, that's in should be in your assignment to work on. This next one, you'll become more familiar again with this one. So the generating function for pi uses these two rules that we've built in. We're going to roll a die that has p written on the side of it, and that is the probability that the node you land on has degree k, right? So that's the number of times you're going to roll the next die, which has rho written on the side of it, and that means if you go out from in these k directions, you'll have that's the probability that the subcomponent out here has size n1, size n2, size n3, all the way around to size nk. And you add all of those up, and you add up your first one, the node that you hit, that's that simple x. That's the simplest rule we have. That just means that you're adding 1 for the initial node, right? So this was a very important rule. We can't solve this. We had the analogous one, which was that f of rho here is x, and it's f of r, f of rho. We could solve that. Okay, so we've got this blob, so let's differentiate it and see what happens. Right, we're trying to get the first derivative of the generating function, and we're going to set x equal to 1. So let's do that. A little bit of pain. We're going to go through the pain. But there's a very important thing that happens around critical points in systems, whatever they are. We're talking about networks here, but it could be magnets. It could be any system that has some sort of critical point there. We'll see a very interesting piece. Okay. All right. So we're going to take a derivative of this thing, right? So it's a nice looking beast. It's just a simple x there. So we have a product rule. Differentiate that. You get a 1. And that rest of this stuff is here. And then leave the x and differentiate all of this. And it's a chain rule, manifestly. Yeah. So the thing in the middle comes out the front with the derivative, f rho prime. And we take the derivative here, f prime of p, and then the blob is still there. Yeah? Old school, generating function. Yeah, chain rules are great. All right, and we had this one, which we haven't really said. So we see we get the derivative of the rho generating function, so we'd like to know something about that. Here's our second connection, right? So we differentiate this one, same idea. Now we're going to get the first derivative here. We're going to set x equal to 1 at some point. And we'll be very happy. So let's do that. So we're going to set x equal to 1 here and here. This will give us the average component size, right? You jump on a node. This is the average component size. We jump on a node. This is the average size of the subcomponent. Sorry. If you run along a random edge, this is the average size that you see at the end of that edge, providing the average size of a finite component. So there's some probability, if there's a giant component, that you'll hit a giant component, and that doesn't count, right? That's just excluded. You get a 0 for that. That just doesn't go into the calculation. Tricky thing. It's a sneaky thing. Forward browse. We're back into some pain, I realize.
I just have a quick question, sort of related to this. So we know that the mean of the first expectation of some distribution is the first derivative of some function f evaluated at 1.
Yes. Right. You don't want to say the generating function? All right. Mm-hmm.
The first expectation is also the integral of the probability distribution. X, so change variable to x is the integral of x times p of x.
Mm-hmm.
We have an integral of something equal to the derivative of something else. And those two things are equal to the derivative. Is this in any way related to what you work for?
Well, yeah, yes, but yes, we can talk about that later. There is a thing you can do with that. Mm-hmm. There is a thing you can do with that. Yeah, you can do it. Why not? Yeah, of course. Yeah. Insanity, right. Because, okay. There is a way of treating because you can make a simple poll. Say, you want the nth moment, for example. You could, and it's a da-da-da-da, that's going to be, yeah, anyway, all right, okay. Good, all right. So we're going to set x equals 1, and then we'll have the thing we're after. You can see there's some good stuff in here. This is f of rho evaluated at 1, which isn't, normally that's 1, right? Generating functions evaluated at 1 is 1, because it's the sum of all the probabilities. However, this is an odd situation where these are very special distributions, and they are the probability that are to do with finite components. And so there's some probability that you're not involved with a finite component. There's a giant component. So, for instance, this, where is it? We don't have f pi. Where is it? All right, well, we'll get it. All right, so we can solve this equation here for this beast, right? F rho of 1, F rho of 1. It's here. These are just numbers. This is just a number. This is a number. This is just a number. Undo everything. We already figured this out because we were looking at the probability that if you run along an edge, you get to a giant component or not. Right? That's what this beast was about here. I know. And you can plug this back into here, this beast back into here, and you'll be able to x is 1, x is 1, x is 1, blah, 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 and we'll get this thing. All right. So in principle, we can do this. Okay. So let's work through a couple, and then we'll be able to. Okay, standard random graphs. Lots of good things happen with that because, again, we have these Poisson degree distributions, and we have this odd thing that the probability that a node has k friends is the same as the probability that a random friend has k other friends. Right, and that gave rise to some mistakes that people made that didn't matter. All right. So our two equations collapse because we only really had one, so we only need to look at one of them, and we can replace every pi with rho and every rho with pi, whatever we want to do, and now we've got just p's and pi's. Okay, good. And we're going to undo this thing. We're still x's. We're still hanging around with x's, right? So we took the derivative, and we're trying to get this blob. So here it is. Here it is. So we bring this over to here, and then divide through by everything that's attached to it. There's a 1 here, and there's an x, and then all of this blob. So that's 1 minus x, this blob. All right, and we're going to bring that over onto this side, and this has been sitting on the right-hand side the whole time, so here it all is. So everything is there, right? This is the generating function for just the degree distribution. Here's its first derivative. This guy we have figured out, apparently. And we are going to avoid putting all the x's in. We're just going to set x equal to 1 in this. We can help ourselves a little bit because we have special property again. This is the first derivative of the generating function for the degree distribution. Let me write it. Let me see if I can get this thing to explode. Yeah. And so it's f. Right, f of p of x is e, let me get it right, it's k. How do I usually write this? X minus 1? 1 minus x? That's wrong. That's right, so like this. Okay, yeah? So we're going to take the derivative of that. Boom. And we just get the same thing back, so we can see this, right? And this is all connected to why it's f of rx is f p of x. All right, so that's just a little calculation there. Good. So we're just trying to get rid of derivative, make it even simpler, so this derivative can go away. We're going to replace it with a nice, healthy thing. I know this is algebra. And what have we done with this one? Yes. We know FP, right, this thing has been sitting here the whole time, and that's sort of this underlying functional relationship. right? Back here, all of this stuff, right? We can replace all of this with f pi of x. So this is just a little bit of sneakiness, right? And it's only okay when we have Poisson degree distributions. Right, so we're going to use this, here it is. We're going to use this main story, which is only true for Poisson degree distributions. Right, this is our basic thing. And that was f pi, but now f rho, now it's an f pi, because again, Poisson doesn't matter. All right, so we're going to change that. There's an x equals 1. If we said x equals 1, x equals 1, x equals 1, this will just be f pi of x on the top. There'll be an f p of x just here. Okay, I know. Lots of concentration. And then we have our big story, which is that the generating function for the pi distribution, right? Again, this is the size of the finite component at a node, a randomly chosen node, is 1 minus the fractional size of the largest component, which is the size of the giant component, the fractional size of the giant component, right? This business here. Right. Here's S1. This is the story for Poisson ones, right? So this is K critical in this case is 1, right? Boom, takes off. All right. So a little more algebra. The end result, this is the thing we're looking for, right? When we set x equals 1, this is the average size of a finite component. Take that derivative, set pi x equals 1, so it's going to be 1s all through here. So the top ends up as 1 minus the fractional size. We get 1 minus the average degree, 1 minus the fractional size again. So you can work through that to see that that's true. And then let's look at this. This is the thing we tune, right? So we tune the average degree, and that changes the size of the giant component. So we're just going to look at this a little bit. This is sort of the key thing we're trying to get to. It's just the size of the finite component, right? So this is something that's at least 0, but this is not normalized. This is important. These are fractions, right? So this is between 0 and 1. This is some number. It could be 33.2, right? It's just take all the finite components. What's their fractional size? Sorry. That was not quite right. You randomly select a node, find the size of the finite component it's part of. If it's part of the giant component, then it's 0. It's not part of a finite component. This is an important percolation problem. You could take all of the components and average them. That's different. Because now we're saying each component gets sampled every time at every node inside the component, right? That's different to saying here's a component. This is again like the rich gets richer story, where we're either sampling by the city or by individuals in the city. Get a different weighting. Okay, so bigger components get weighted more. All right, so we've got this thing. So for Poisson, the classic result, right, is that the average degree of, having just simply an average degree of 1 is where you get that giant component takeoff. That's the critical transition. And so we can look at what happens below that. So for the average degree to be below 1, S1 is just 0, right? S1 is simply 0. That's this plot here, right? This is equal to 1, right? Okay. So S1 is 0 for all average degree less than 1, so we can just put that in. We're going to put a 0 here, and then we just have this business. So below the transition, this is what the average size of a finite component is. This is, we haven't done anything. There's no approximations. It's technically absolutely true. It's for infinite random networks. So this is all true up until average degree gets to 1, and you see that this explodes. When it's 0, it does the right thing. So when average degree is 0, no friends. Everyone is a island of size 1. So average degree is 1. That's correct. And then it just takes off and explodes. So this is a classic phase transition story. You have something like the size of the giant component. That is what's now called a continuous phase transition. It's discontinuous in the derivative. And people would talk about second order and third order and these sorts of things. There's a discontinuity in some derivative. But now we tend to say it's a continuous phase transition versus a discontinuous one. You can get discontinuous ones, and I might add that, but that's another thing. Okay. Okay, so what's happening as you get closer to average degree of 1, you're getting a power law size distribution of components, component sizes. So, and then eventually the biggest one just goes, just as you hit that transition, go a little bit, it goes glob, and it's noticeable. You can see it from space. You look at your random network from space, and you can see a little blob, and it's just a little spidery tendril right at the transition. It's a fractal kind of object, and then it has some substance. And it's slow, right? It's slow. I mean, it's this thing here, I mean, as you go past that transition, there's just a tiny little thing. It's a giant component, still infinitely big, right? 0.0001 of infinity is infinity. So it's still there, it's still a thing, and it gets bigger and bigger. But what's happening at the same time, let me sketch it in, is this is the average component size, right? So it starts at 1, I got that right, and goes gaboosh, which is a technical term, and then, right, there's it explodes. So, and it's true on the other side, right? It's actually true on the other side. So the average component size goes to infinity, finite component size. Right at the transition, you have this kind of tendrily structure, and this is true, for water and all these things. And then on the other side, it's still finite components, but you've got a giant component, which is occupying a lot of it, and then more and more of it. But you can still talk about the finite components. They're still there, so they're just hanging around the outside of it. And they have an average size which decays away to zero, to zero on this side. Right? Eventually, everyone's in the giant component. So it starts at 1 and goes away to 0. So this is a classic structure. It's a way, you'll see in some papers, some people's works, that this is the way to getting to where the critical point is. They look at when the average degree or the average magnetism or the average whatever it is explodes. They look to find something that explodes, right? Which is cool, but it's just another approach. So lots of aspects about systems like this might go crazy. And so this is, if you've got something connected with component size, then this is a big deal. This doesn't look like a big deal. And if you think about things spreading, well, it's kind of true. It's not really big. But this shows you that, in fact, you're getting some enormous component sizes in there. I mean, it's an infinite network, so that's why when they're normalized, you end up with, wow, it doesn't look very big. But it is reaching an infinite extent of an infinite network. All right, that's a kind of a classic thing right there. That puts us there. Typical critical point thing. I guess I said this. The limits of 0 and infinity for the average degree makes sense. So as the average degree goes to 0, then we get the average degree, average component size going to 1. And as this goes to infinity, right, this is starting to dominate. This is going towards 1, though. The size of the giant component is going to 1. So, and you could think about this in various ways, but basically this whole thing is going to 0, which is good, right? There are no finite components. Every node you jump on will be part of the giant component and gets a 0. There are some extra things, so you can really get excited about this with the math, and you probably think it's too excited already, but right at that critical point, you can start to look at things like this. So how does the size of the giant component scale? Well, it scales like n to the 2/3 divided by n, right? This is not the infinite limit. If you've got n nodes and you're letting it grow, then you get this thing. So it has a fractal story, and it's in fact this. And you can find all sorts of things, right? So for average degree, actually less than 1, the largest one grows like a log. There's some log things involved, which is 0 for large n. It's not big. Okay, so there's all sorts of stuff to play around with. I'm just going to zip through this and show you. We had this example, right? So we're just going to have degree 1 nodes and degree 3 nodes. Yeah, sure.
Going back
Yeah.
to the slide.
Which I didn't do. Yes?
So for k equals 1, if n is infinity, for the top equation, 2/3 over 1.
Yeah, so this is limits. So it means it takes up 0 space. But it's tendrily, you could sort of see it's a gossamer kind of structure, right? So it's on that edge, and then as you just move below, it goes into this sort of thing. You move above. You know, what really happens is you have a power law size distribution that has a cutoff, and that cutoff typically, to be honest, I'm not exactly sure, but usually it's just the power law that grows and grows and grows, grows and grows and grows, and then really is a power law right at the thing, and then starts to truncate again. So it's not as if, you know, there is a sort of a smooth thing where it's going to infinity, you know, and it's just sort of, the critical point is a big deal, but right next to it, you know, it's a lot of stuff going on as well, right? You know, self-organized criticality, we talked about this, right? So the idea that systems somehow get naturally driven to that critical point. There's that sandpile model that we talked about, which mathematicians now study in very abstract ways and don't even know that per bark work, apparently. They have negative sandpile heights and all sorts of things. This is, you know, this one point, this one special point. Like, why would it be at this point, right? The observation was, well, you get power law size distributions. That must be what the universe is doing. Yeah. So you wouldn't see it from space. I mean, you just sort of see the edge of it just as you do with a fractal. You'd say, oh, it's like, but it wouldn't be solid. You'd see this tendrily structure. Yeah. It's not bad, end of the 2/3. It's not bad. Let me quickly give you this. Sorry, yeah, end of the 2/3 unnormalized, yeah, right. Right. Yeah, the normalized one, yes, end of the minus the third, so it's decaying, decaying, decaying. Same problem, right? This is everything. We've set x equal to 1. And we're trying to find that average size of the finite components with that degree distribution. This is a much simpler thing. We solved it, you know, I mean, even though there were square roots and all sorts of weird things and Taylor expansions. We had these stories, right? Okay, this is we'll have this sort of thing again in a different kind of way, but right? So once again, this means there's half a chance x to the 1, right? That you find that your randomly chosen node has degree 1, half a chance that your randomly chosen node has degree 3. This is how many other friends it has. There's a quarter of a chance that an edge you're running along hits a node with only one friend, and then, which is you, so it has 0 other friends. 3/4 of the time you'll be hitting a node that has 3 other friends. That has 3 friends, therefore 2 other friends. So that's that 2 there. So we can put all of these things in, we can differentiate them, blah, blah, blah. We're going to stick them in because we'll need fr of x here, f prime r of x here. You know, basically you just do the work, right? So we just do the work, and I'll just tell you what happens. So we're just sticking these things in. We had this result before, that you get a third, right, for the f row of 1. So that's the probability that you're running along an edge that you reach a finite component, a subcomponent. 2/3 of the time you'll actually be in the giant component. 1/3 of the time it'll be finite. That's from before spring break, so I expect you to not remember it. But we're well above the phase transition here, right? In the assignment you're working on next, there's a phase transition you're trying to find out as you dial the balance between degree 1 nodes and degree 3 nodes. All degree 1 nodes, no phase, there'll be no giant component. All degree 3 nodes, manifestly clearly a giant component situation. They're balanced here, and it turns out we have a giant component. So we're just going to stick everything in. We're sticking everything in. And then we do some messing around. Right, that's to find f row prime of 1. So that's the average size of the finite component you reach along a random edge. Now we want the one that we get if we just jump on a node. So we're just sticking all these things in. I believe these numbers are right. You could check them for me. It's pretty ridiculous. 122 over 27. So that's pretty small, actually, right? So on average, if you found, not average, the average size of a finite component that you find when you jump on a node is, right, just a bit over 4, or close to 5. It's not very big. So there are these little ones, those 3s have to be capped, right? That's their problem. To not be part of the giant component, you have to have a 3 that has 1s on the end of it, that's just a little blob like that. Or if it's got another 3 here, they have to be capped and so on, right? Otherwise, they're in the giant component if it starts to run away. So, anyway, so these are things you can figure out. These are things you can figure out. All right, okay, that's good. So, generating functions, we are through them, but you can work through this stuff. It's good stuff. Very odd business, but it allows us. It's a little magical, a little odd, but you really have to. Once you've got all the things in your head, you realize what's going on. Setting something x equal to 1 and for a particular generating function will make complete sense. It's like, oh yeah, of course. But it's still weird. It's still a weird business. So they're useful for contagion as well. And I'll show you, I want to come back to this. I want to emphasize that you can get the really good basic results out without generating functions as well. And when we get to the Gleason work, which I presaged somewhat in Principles of Complex Systems, which is really beautiful stuff, you'll see it's a different story altogether. And we really do actually get into the giant components there, which is very hard. That's a very difficult problem to solve, a very, very strange, difficult problem. Okay, right? Because we know in these giant components they have loops, and that's a problem. With these random network calculations have always been about just that there are no loops, right? That's why we look at the finite components, because they're completely trees. They're just pure trees, and we can enumerate them and count them and play around with them, and then say something about the stuff that isn't a tree, the giant component. So it's always been it's been a sneaky business. We've been avoiding the interesting thing. We can find the size of it. Anyway, we'll get to that for contagion. We'll come back to this. I think that's a pretty good introduction to generating functions. We're going to, maybe I shouldn't use those words, but it will, I'm going to show you some more of it for random bipartite networks. We have to do that. It's a very nice thing. So there's going to be a little more. We'll use a lot of the tools we already have, but hopefully that should help you with this Ethel the Frog assignment. Okay. All right, so oh no, I don't need to do that. Let's go to this thing here again. I know I'm in the wrong spot. Here, yes, good. The problem with this is I don't have indices. We okay? All right. Here's a funny thing to start with. This just got published so yesterday was Pi Day, right? There was some excitement about Pi Day. There's always excitement about Pi Day. I wonder if people would care in 15,000, right? That's going to be kind of a big deal. Although, that's true. Pi Day is only a US thing, isn't it? Yeah. Yeah. What do the Canadians do for dates? I mean, they've got the Queen on the money. They've got the metric system going on, right? They don't mess around with the. Do they? Yeah. Anyway, all right. So it's very special. Okay. So it turns out. So this is bizarre. It turns out. So there's a result that just appeared, made the news yesterday, that prime numbers, which people care about, right? They've spent a lot of money, or time, maybe not enough money, time thinking about them. But it matters for encryption, so there really is some big time investment there. And there's a lot of evidence about them, a certain amount of randomness in them, right? So, and that's been around since the 30s, and there became a presumption in that the digits were just random. There was nothing special about them. And I don't understand how this was not known until recently. Just sort of found out. One of, I guess, that came from, I think the stories that came from looking at, and you can follow this article. It's over on. It's not Wired, it's somewhere else. Started from looking at primes in base 3, right? So the digits there, and we've talked about Benford's law, right? The first digit story, and how that doesn't matter what the base is, and it's this funny thing that's the first digit, of course. So we've known about those kinds of things, so we might as well look at it. Turns out the final digit in primes, and this was, again, in base 3, it's evenly balanced. There's an even weighting of the ones that can be the final digit. And so for base 10, it has to be 1, 3, 7, or 9. right? You have 2 and 5 for the smallest primes. But for primes in general, 1, 3, 7, and 9, that has to be your final digit. And it's about, from what I understand, this is a quarter, right? So if you get all your primes, or just an enormous number of primes, and then look at their final digits, you get about a 25% balance of them. However, if you go from prime to prime consecutively, and look at what the digit, and this is a classic kind of dynamical systems thing, right? We're here, what's the next thing? What's the next thing? Can you predict it? You know, xn plus 1 as a function of xn, chaos, classes, dynamical systems, love this sort of thing. How many rabbits are there this year based on how many rabbits there were last year? Well, so it turns out that it's not random. There's a bias. So this is sort of this big, craziness. Now, okay, so that's very interesting. Obviously, they're going to open up all sorts of boxes there. I don't quite understand what's going on with number theory because, this thing with twin primes and that story is sort of, maybe there's canalization. I mean, people are sort of just digging in the wrong place, like they're all following Terence Tao and other various gods and so on, and they're not, kind of exploring everything. I mean, that's how science works in general, right? The twin prime thing was a lecturer at the University of New Hampshire, couldn't get a job, and just spent years, I think also working at Subway, right? Just spent years obsessing over this particular sieve. It was a sieve that, like the classic Aristophanes sieve, figuring out ways to get primes that are spaced, 2n apart. Anyway. Of course, once that sort of comes to light, everyone runs over there, right? It's like, oh, okay, and they, dig it apart like piranhas. So that's probably going to happen here, I suppose. It's just like, how did you not see? I think it's funny, right?
When they got the University of New Hampshire, they had a bound on the twin primes, and it was pretty big.
Yeah.
And that was like one of the first times Terence Tao did like the crowdsourced.
Yeah, then they crushed it, right?
And in 2 years, they brought the bound down to like 40 or something.
Yeah, just like, but they knew they found the vein, the vein to go into, right? Yeah, right. I don't know what it is now. It's getting close. Yeah. Okay, so in the middle of this article, which is sort of crazy and interesting, there's this little aside, just saying, ha, no one understands probability, right? Which I like to talk about, and we had the shell game thing and the girl born on a Tuesday, right? So, all right, so let's think about this. This is random walks again, right? Random walks are everywhere, right? So, but tosses, okay? So we can imagine, this is a coin. This is a random walk. So you either go up or down, right? And it's left or right, whatever you want. But on our little plot, time is going this way. You go up or down. So that's maybe a background thing to think about. We'll draw some pictures. So what's the probability of flipping 2 heads? We're going to flip a coin twice in a row. Nothing special. It's a good coin. 2 heads. Head. This is the order, right? Number 1, number 2. Probability is 1/4. Head, then a tail. Also good. Okay, so we're going to flip it many times. And what's probably the last 2 of them are head.
1/4.
Mm-hmm.
1/4.
Yeah, good. So solid. Okay, so now this is just that you guys can just guess this. I mean, just sort of guess this. So roughly kind of maybe we can talk about it a little bit. So we're going to stop when we get a head and a tail in that sequence, right? So it could happen it could happen the first 2. So on average, how many flips do you think this takes?
But then you would be showing it to us. Is it
No, I don't know. Why is it 4?
if it's a quarter probability to see the sequence
Okay.
on the 4th flip, although
Well, if it's a
Not bad.
probability in the sequence, then you have the geometric probability distribution.
Mm-hmm. Yeah, which would give you that. Flip it up. Yeah, that's good thinking. Yeah, very good. Yeah. Seem okay? All right. Yeah? Well, okay. But not too many, not 30 or whatever, but maybe.
I don't know enough probability to
No one does. It's all right.
really say what I mean, but like originally I thought 1/4 because that we have the sequence.
Mm-hmm.
So
Well, all right, so what about this one then? All right, same thing. Maybe, or the average number might be greater than 4? Well, let's ask this question. Okay, so we've got some, we're not, okay, so it could be longer. What about this then? What's the, on average, how long does it take to see a head then a head? Same thing? What does your intuition tell you? What is your intuition tell you to start with? I mean, it tells you it's probably should be the same, but why do you feel it's not the same? Well, the intuition you have to develop is that your intuition is always wrong. That's the 3? Quicker. I mean, should it be different? Why do you think it's different? That's sort of that's going to be the main question.
Because each flip is an independent event.
Yes.
Seeing a particular sequence in the running probability is not enough.
So which one should be larger then? Which one should take more?
I don't see how they, even with running, I don't see how they could be different.
I mean, they're both a quarter, right?
Yeah.
It's disgusting. Yeah.
So it just feels different though, because like a tail is a failure.
Okay.
In one sense.
Here, you mean here it's a failure?
Running along, you have a tail, you kind of fail on that one, and you fail on both of them, right?
Well, this one, I mean, you're getting at something. Yeah. Conrad, what do you want to say?
So that the head tail that has to follow, if that followed a tail, that tail would have to follow another tail.
Okay, so this is the thing. Like, what are the possible ways of getting to this?
Exactly. So there's few more maybe to get to there, except though no, for HH, the only tails can be before HH.
Right. So you know, unless this is the first two, you'd have to have a tail before that. You could have right? This could be a head or a tail before it. So now we're getting a bit of a difference there. So you're starting to see a difference. It's still upsetting, I think.
Wait, so, I mean, if we're thinking about it, like a tail is a failure, I mean, we have branch prediction in computer science. It says if the branch was taken on the previous run, it's likely to be taken again on this run. But those aren't completely random events, so I don't know.
Yeah, these are independent. They're absolutely independent. Yeah.
Then I guess I don't see how they're
I mean, one argument, one way to start saying is that, let's say both of them have to start with a head.
Sorry, is that well? So the sequences that are before them, the first one, the only sequences that can be before that are ones that are big strings of tails and single heads, right?
All right, that's good. All right, so let's
And then the one before the heads can be
okay. So head, tail. All right, so head, tail. So bad. So head, tail, right? So if we think about it like random walks, this is going to be, and heads are up and tails are down. Then this has to be a walk that does this. That's when it stops, right? So this is our stop. So we're imagining random walks, and as soon as you get a little up, down, then it's a stop. And this one, the other one has to be like this, right? Head, tail, head, and that's a stop. I mean, it's still very strange, right? So then you get, whenever you get two heads in a row, you'd stop. So to avoid, so for this one not to turn into head, tail, as soon as you get a head, it has to be head every time. Because as soon as you get a tail, then that's your completion. So that's a thing to think about this, right? So before it can be heads, and before that can be tails. So this is the start. These are possible sequences. And so this is a beautiful little combinatorics problem. Like, how many of them of length n are there? right? So if this is going to be length n, then there's going to be length n minus 2, right? There'll be n minus 2 here because we have to end with that. And we're allowed to have as many tails, we're just continuous tails, and then contiguous heads. Can't have anything else. Right, so one way to think about the walk would be, it could be tails, and then heads, like that.
Yep, it could be all tails, and then the first head, and then a tail.
Right.
And any combination there.
This one.
And all heads, right, yeah, exactly.
Right. So there aren't so many of those, actually, right? There aren't as many of those. And another thing to think about here, the big deal to think about here is, and I sort of said, I suppose, is if we're going along and we get a, yes, so we're going along and we get a, we've got a head and we fail, right? We don't get our end sequence, we get another head, we're supposed to get a tail, we get another head, then we've got a chance straight away to finish. This is the really crucial difference. Going along with heads, so as soon as you get one head, then it's kind of the end game, right? This thing will stop as soon as you get a tail. So every time you fail to stop, you're always set up to end the next flip. However, for that one, so you're going along, you've got a head, but then you get a tail, you have to start again. There's always 2 steps. As soon as you get a tail, there's always 2 possible steps. So the possible situations for this is a whole bunch of tails. How many? This is the harder calculation, actually. So tails, right? Tons of tails like this, and then isolated heads in here. You can't have 2 heads.
Would it make sense? Could it
Yeah.
be a lot easier to solve if you model with Markov chains? Because then you have this state of tails, you can keep going to tails.
Oh, like the thing?
Heads, but once you're in heads, you stay in heads.
Yeah.
And when you set it up the right way, it'd be really easy to solve.
So that's a good question. I mean, it's not a bad little code to write, actually. It's a kind of an interesting little piece of code because you can do it in good ways, bad ways, right? Right, how do you do that effectively? I mean, you could write a little loop, and as soon as your condition comes along, or you could make something more clever, I don't know. But, yeah? Pretty weird. What's that? Yeah, so I didn't solve it analytically because I ran out of time, and this is what we're getting to. This is what you need to do. What's probably of finding the, right, if we want to get the average, what's probably of getting an HT on the n minus 1 and nth flip? Because you need to know that distribution, and then you can average over these probabilities to find the average n, and the same thing for this one. And so I just made a simulation for it. So we could think about. I think this is right. Right. So there's a quarter of a chance that both of them stop after 2 flips, because that was our first observation, right? There's nothing special about that. But then the head-head one gets into trouble. It starts to take longer and it has a more skewed distribution. So the averages are about, well, I think they might be exactly 4 and 6. So your first statement seems to be right on the money. But we couldn't see a good way for the head-head thing. But it requires, so a nice way to think about why they're different is that the failure for one, for trying to get a head-tail, failure for one means that you'll get 2 heads in a row, but that allows you to succeed in the next step. Whereas a failure for the other means you're at least 2 steps away from succeeding. So it gets pushed. And so, so there's a quarter of a chance. And if you haven't, so these ones, you have to think about this, these aren't all possible sequences make it to here, right? So head-head, that's finished. So these ones the ones that get to this one can only be tail, head, tail, tail, or head, tail. And only, what did I say, tail, tail, head, tail. Yeah, and then tail, head, that could be the one that would succeed, right? It's disgusting. And it was just a little sort of throwaway paragraph to say, ha, in the middle of this, in this paragraph. Yeah. But actually, what it was, to be honest, this was the inspiration for, someone saw a person giving a talk who was doing the ha to the audience, and one of the two people involved, and thought, oh, I wonder about, and went off into, and there's a comment from some other professor in the thing saying, I don't know how they even would have asked this question. Which is getting at the whole, like, how would you have this hypothesis? Like, just, I don't know, just go and explore the thing. That's what people do. I mean, anyway, so pretty weird though. I read that paragraph, and Scarpino did the same thing, because we sort of started talking about this in the morning, and then I tweeted about it, and he's like, wow, and we just come on, and he's like, okay, sorry.
So, with how to solve it, my first thought was automata.
Yeah.
Are there any interesting ways to integrate common reports into that so you can figure out?
Yeah. So you could, short of actually just doing it analytically, you could kind of, you're almost doing it analytically, but you could turn it into, it's kind of almost getting to be. Here's one thing that if you're trying to avoid, and I don't know if this would help with your automata, but if you're in here, right? If you're going to say this is n, there's going to be n minus 2 flips in here, right? We're going to we want to count how many possible ways there are to end up with 2 heads such that there are no sequences of more than 1 head in here. And a way to think about this, and we'll come back to this later on, is that the tiles the little tiles that could go in here are t's and head t, right? So they have to be like this. So instead of thinking about making counting it by saying, well, it's t's and h's, the only things that could be in here are these are the only allowable sequences, t's and ht's. Because right, you'll never get 2 heads together. And it means that this last one has to be a t as well. It gets a bit tricky because if this is 37 in length, then you have to think about putting together so many things of length 1 and so many things of length 2. So you might not be able to put this at the end, and so you have to count. You have to be careful with your counting.
That's nice, but more intuitive is you can really just say where there are eligible places to put 1 H on all of them.
Yeah, how do you exclude them from each other? How do you make sure that?
In case where there's 1 H, then there's no put an H.
So 1 H is easy, right? Yes, you're right.
Just pop it through. Then you can put an H in
2.
an arbitrary place. So then you can go up to 1 thing before.
Okay. And what about 3?
Then two H's in an arbitrary place.
And then exclude the.
So 1 thing before, 1 thing after, 1 thing before.
Oof. Ouch.
So you could, so that's
See if you can do that.
not as pretty as that, right? I mean, that's you're putting the H.
We'll see when we get to generalized contagion. This is something that I had to figure out. Actually, I figured this out to solve it. So and it was nice to sort of see this. That's the way to think about this. And when you're talking about here, it's different, right? These are all T's. These are all H's. And then it's just you dial this part. Yeah, that's all. But you can see, so as soon as if you're trying to get to an HT at the end, as soon as you start, if you start with an H, they've all got to be H's. You can't turn it off, right, before you get to this end part. This one, there's a lot more sort of like roaming around with random walks, yeah. But there is this random walk analogy, right? So that's what the stopping conditions are. It's like going up and drop, that's the end of it. This one, you go up twice, and that's the end of it. But still, I think very strange. All right, so do we accept our silliness? I think so. All right, I'm going to set this up, okay? I know there'll be sort of just the generating functions, one more week of this, today and Thursday, and then we'll be into other sorts of things. There's a lot of other stuff we got to get to. I mean, contagion we're going to go through. There's going to be centrality, assortativity, structure detection, lots of other good things. We'll get to maybe some stuff on organizational structures. Anyway, all right, good. Okay, random bipartite networks. So what are these things? Okay, so here are a few examples. I mean, there are bazillions of examples. So Bagro is part of this paper. I think it's done, and it's a Barabazi paper. It's done well for citations, but got an unreal number of downloads. I mean, like hundreds of thousands or something. It's like maybe the most downloaded paper from its scientific reports, but from the Nature website. And there was a similar paper by Lado Adamic and Urulin and a couple of other, or at least one other person, similar kind of thing. So they trawled through, in that case, recipes and the ingredients, right? So you have recipes and ingredients. So this is a bipartite affiliation graph. You're making products there, but you can think of all the ingredients here and all the recipes here, and then you draw these lines between them. And the idea out of this is to say, okay, here are all these affiliations, and it could be boards, we'll talk about that, and directors. You sort of put the boards here and the directors. What does that imply about the networks, right, of boards and the networks of directors themselves? So this is a really nice way to think about a lot of social phenomena. And in this case, it's actually the compounds inside ingredients, right? So we're getting into words that we can't say very easily. But these are ingredients here, right? So garlic, tomato, parsley, olive oil. And then linking them based on their compounds. We have people with biological knowledge who are wondering what's going on. And their big story here, I think, was that in Western foods, and sort of, it's maybe no surprise, that foods are paired with similar compounds, and in Eastern, they're paired with more, it's like sweet and sour, right? They're paired with more opposing kinds of things, and you can see it in this detailed way. And of course, lots of data. So fun study. They got the whole thing in there. But these are, seasoned mussels and shrimp, scampi, and tomato broth. So there's the recipe, and then they dig further into the thing. So there's a lot of work on this sort of stuff, right? This is just digging more into it. These are then connections of the flavor network, right? So this is ingredients here in this case, right? So we've gotten rid of all of the little tiny bits, right? What they're made out of. We've used that to then create an ingredient network, right? So again, like boards are connected by the directors that are on them, and directors are connected by the boards that they're on, or movies and actors. We can say that these actors are connected because they're in the same movie. And these movies are connected because they shared the same actor. And you can talk about the strength of those ties and so on. And there's going to be some messing around to make this, shows only the statistically significant links, and so there's some details in how this thing is made. But it looks pretty good, and so if you get into it, so here's the fish section, right? This is great. Usually I can never see these things, but it's a good enough projector. So fruit over here, right? Plums and apricots. Apricots in Australia, really good. Turns out it's just like Sicily, I guess. So here's tea, and then under cocoa over here. What else have we got? Alcohol? Where's alcohol? In here? Over here, right? Yeah. Apple brandy, I think that is. Is that what that is? Yeah. Cognac. Must be cognac. This is great. Vinegar's hanging off over here. Not quite alcohol situation, right? Yeah, fair enough. Olive oil and this sort of stuff. Is that lard? Lard is hanging out over here. 1950s or 1980 or like 1850s recipes of lard would be just like boom right in the middle. But yeah, it's kind of we've expanded a little bit, I guess. Yeah, and there's some nuts hanging around there here by themselves. Anyway, lots of fun to look through these things. Cheese, the cheese section. It's great. Yeah, and then categories, all these things, prevalence, right? So they had a great time, did a great time. All right. YYN, he's a very, very smart guy. So he's at Indiana. This is, right, so this is the Adamic one. Yeah, right. I forgot I did actually have this in here. So this is a different business looking at, again, online recipes, looking really at their ingredients. Yeah. See a big separation there, actually. Yeah, cool. Hidalgo, Cesar Hidalgo is sort of famous for this work and many other things, but this is sort of his big story. We talked about Pantheon, right? The Pantheon project, which is looking at the cultural products of which is really people generally coming out of countries, and there were soccer players and so on up to scientists, and the highest level was video game directors, basically, right? Beyond movie directors. So that work came after this. This was an initial piece. This was with Barabazi, did his PhD with him. Cesar's now at the Media Lab. And this is about the products, right? And this is one of these graphs that, networks has been sort of messed around with a little bit. There's some more horrible version of it underneath, but it's been tailored to look okay on a page. Basically, the things are adjacent to each other if countries tend to produce them together, right? So there are places that produce oil and nothing else, for example, right? And there was this sort of sense in that paper that you would move more and more into this region of the thing, into the center of it. Over time, they looked at Chile, because of where he's from, and South Korea, I think. So you could see them, countries generally kind of starting to colonize this thing, and it's more electronics and the more complicated things in the middle. So that's another good bipartite thing. This is a paper from Science. Where was that one? That was Science. This is a Science paper from, 2005. Brian Uzi's part of this is a Northwestern group looking at creativity. And so so there are 3 collaboration stories they looked at. So of course, because we have all these online repositories, the archive for physics and these other areas, so I think economics is in here, yes. Looking at co-authors, right? So you have a team of co-authors, and then they might write another paper together, and maybe they split up. It's like bands, right? The drummer dies, and you have to get someone else. Explodes, chokes on his own vomit, that sort of thing. Although sometimes you're not sure whose vomit. Sorry, that's Spinal Tap. Not making this up. They made it up. Okay, and they looked at Broadway musicals, actually, right? So you have a creative group there, people who wrote the thing. And then looking at how the turnover and all these sorts of things, people have looked at this now in different ways in World of Warcraft, and it is like bands, right? You need different people to fulfill different roles. So that's that's another thing, right? People and teams. People and teams is a dynamic one. They had a mechanism for how it might work, right? I mean, we're not going to go into massive detail, but you can see this kind of nice little, physics-ish kind of model. I'm not going to say it totally works or anything, but it's because I haven't really studied this one in depth. But this is the idea, right? You have newcomers, people who are already there. There's some probability of joining a team, moving from a team. I mean, it's a very appealing piece of work. This is diseases and a connection through genetic links is really what this is. It's Barabazi. But again, a bipartite story, right? So you end up with the sometimes called the unipartite or the projected network in one direction, right? So you have this affiliation, you have the boards and the directors, and you project that structure down and find out who's connected to whom. So. And it can be very powerful. I mean, especially if you get enough data, you can say, and here are these clusters and so on. And we saw that with the food one to start with. They emerged. You got these nice clusters that made sense. So you can go and then study something like this, which might be more complicated and weird. And we don't have such. We eat food. We know something about food, hopefully, so people can say that yes, all right. Yes, that's right. So this is an interesting piece appeared in 2014. And so it's the complex networks people, some part of our whole sort of group of people that work on this, physicists, looking at, and we talked about primes just now, but looking at primes. And so the idea here is to, so you've got a composite number and you have all of its prime factors, and then starting to build a network out of it, right? So 2 as a factor, right? It's got 4 links into 16. 19 has no friends, right? 14 is connected to 2 and 7, so you start to build a network. And so they found out various properties. So scale-free networks emerge, and da-da-da-da. I'm not sure that it advanced. I'm not sure if it does. I think it sort of is an analog for some stuff that people have figured out through very different kinds of paths traditionally in number theory. But there you go, networks for prime numbers. Okay, so this is the paper we're going to work through. It's a great paper, famous paper, 2001. Let's click on this little bit of silliness here. So it's, yeah, 3,000 citations, doing pretty well. Knocked out 300 last year. Mark Newman, who is very good, currently sitting on 108,000 citations and an H-index of 86. So well done. Yeah, I mean, just incredible, just a machine. So, you know, let's talk about this. So this is a well laid out story. You can imagine these are the people, boards, you know, and I've touched on these things in POCs and so on. We're going to actually go in and really look at the mechanics of these random bipartite networks. You remember we used something like this for small world search. Okay, so the game is, so you can imagine you make this more probabilistic, but the game is if two individuals, and we'll talk about individuals and groups, say share the same group, then they are connected for sure, right? Doesn't matter how big the group is, and of course they could share more than one group, right? Which, you know, naturally would make them more likely to pair. But the simple way that to start with is just say, okay, at least one group, then they are connected. So A and B are connected here. All right, let's see if we can see some of these. So A and C are connected because of I. Here's a fully connected graph, which usually means, yes, A, B, C, D, E, right? So they're all connected to group one, right? This is a movie, these are the actors. That makes a little fully connected piece. So random bipartite graphs, there's randomness. There's going to be randomness in what we see, but if you imagine that you broke all these links here, this is what we're going to do, you break all these links here and leave little stubs like we had before, right? This is not the network here. This is the network. Well, this is one network. This is the projection onto the individuals. There's also a network of 1, 2, 3, and 4, right? I mean, I'll probably get the words wrong. This is an affiliation structure. This is just an affiliation structure. You know, people can talk about the movies they're in, but they're really connected to the other humans, right? The other people. You over and over get these little cliques, right? Which are hard things to kind of manufacture with sort of some weird mechanism. They just naturally appear because you're in a context together and you hang out. Again, because we're forcing all of these connections to work, you could impose something on top of it, but all of these ones will be connected. So that's a fully connected clique. 2 gives us a clique for B, D, F, and G, right? So B, D, F, and G, boom, there's a little 4 clique. And what else do we have? 3 just has F, H, and I. F, H, and I, so that's just a triangle, of course, for just 3. And there's another clique over here. It's very nicely done. G, I, J, and K. Boom. All very well chosen so that they kind of fit in this nice little structure. Yeah, okay. But let's see, what about this fig one, right? So that's an interesting one. F, I, G. So that was not obvious, right? So that is a little 3 clique. But that comes from a kind of an unusual thing. So F is part of 2 and 3. 2 connects it to G. 3 connects it to I. And I is connected through 4 and 2G. So you can get some other things, but that was not an obvious one. Now as you get to more and more, you know, we'll have many here and many here, and you randomly wire them up, then, you know, the chance of those things go away. But you get all these little blobs like this. The game will be, let's understand if we prescribe the degree distribution just as we did for normal, right, the configuration model where we say we've got P of K. You know, we start with Poisson, but now we allow any arbitrary degree distribution and wire them up. We're going to allow an arbitrary affiliation distribution for the boards and an arbitrary one for the members, and then randomly wire them up. And see if that, so we're imposing a lot of structure, right? We're saying that, you know, character A has been in 4 movies or is on 3 boards. and this board has 7 members, or this movie has 20 actors. We're going to say all those things, but then randomly wire them up and see if the structure that we get out, for example, the degree, so this is odd, right? The degree distribution of the actual actors is like the one we actually see in the real world. Does randomly wiring the thing up do enough for you? We're imposing a lot of structure. So that's a good game. It turns out generating functions will appear again in a very nice, kind of elegant way. There's also a simpler story. If we want to think about things spreading, whether there's a giant, so here's a thing we'll get to on Thursday. Is there a giant component here and here, right? So when we move this down, big network, move it down and we project, is there a giant component of the individual, or are they all atomized? And so you could think about, well, imagine if all of these had degree 1, right? And all of these had degree 3. So not quite what we did before, but they all had degree 1, all degree 3. Then that means there's just going to be 3 here. They're all on one board each. So they'll all be isolated, right? We'll all separate them all off. There'll be a board, 3 members, a board, 3 members, a board, 3 members. So we should be able to show that so the boards are disconnected and the people are disconnected. Right? There isn't a giant component of people and not a giant component of boards. So we'll see that those two things go hand in hand. If there's a giant component of boards, like an interlock, a board interlock, there will be a giant component of board members. Just talking about boards, it's a big deal, right? It's a big deal because that can be a little obscure. It's people are always on these different boards, and they're all kind of connected in ways that are not obvious, right? If you just look at the board for Coca-Cola, it has these people, it's like fine. But then this one's on this one, this one's on this one. What's the biggest structure there? What else can we say about that? So that's going to be a nice game. You could think about, there will be this kind of, that same kind of thing that we had with finding giant components. These aren't really network ties, right? I mean, they're links, but they're not really ties. These are actual bonds between people. These are affiliations, right? They're things they have on their labels. But we'll travel around it like it's a network. So, for example, imagine you randomly choose one of these edges, just as we did with normal networks. You randomly choose one, run along here towards this guy, and then look at how many boards it's on, other boards it's on. So we need that kind of distribution. Same thing here. Maybe we randomly travel up towards this board. We need to see this 3. There are 3 other boards it's on. So there's going to be this out to people. And so that's how you figure out how many, other friends someone has.
It's just like a transform. It's like going to just a different right? That's the point of a bipartite graph. You're proposing making a variable transform to the mirror, whatever you want to call the upper
thing. Well, we'll see. We'll see. We have that very simple little rule that composes the 2 generating functions, because we roll one die, we get some number, and then we roll another die that many times and add them up. That's going to happen over and over again, because you'll say, we'll roll a die and say, this one has 2 friends. And then let's roll the die for these guys and add them up. And that will give you how many other friends it has. All right, so we'll get to that. It's a start, and that will be Thursday. And we have office hours now, so I'm sorry. I know it's time to go. You've had too much fun. All right, I'll bring food again. Sorry. It was dangerous. It was a bad mistake.